This is Incomplete Information VCG Contracts for a Common Agency. My name is Tal, and this is joint work with Ron Lavi, Elisheva Shamash, and Inbal Talgam Cohen. So we all know markets as a tool for the allocation of goods, but we can also consider markets as a tool for the allocation of effort. The theory that models the allocation of effort is the celebrated principal-agent model, where an agent acts on behalf of a principal. I want to take this one step further and consider a more general model where an agent acts on behalf of multiple principals. This is known as the common agency model, and this often comes up in social media, where an influencer works to promote several brands, in online labor markets, where a freelancer works for multiple customers, or on online advertising, where a marketing agency bids for the ad space on behalf of multiple advertisers. A main challenge in this model is the agency problem. There are actions that generate good outcomes for the principals, but are costly for the agent, who acts in his own self-interests. To align the interests of the principals with those of the agent, the principal monetarily compensates the agent with payments. The compensation scheme is called a contract, and it is designed to incentivize the agent to choose a desirable action. The problem of designing such a contract has three key ingredients. One is incomplete information of the agent's action, known as hidden action or moral hazard. It corresponds to the realistic scenario where the principal cannot directly observe the agent's choice of action, only its resulting outcome. For example, advertisers do not closely follow the marketing agency's real time bidding process, but they do observe measurable outcomes like clicks. The contract thus depends on the outcome, and the outcome serves as a noisy indicator for the agent's choice of action. Second, we enforce two standard properties of contracts. First is limited liability. It means that payments flow from the principal to the agent and not vice versa. Equivalently, it means that the payments from the principal to the agent are always non-negative. And this is a form of risk averseness of the agent. It captures the case where the principals, say the employers, have deep pockets and cannot monetarily punish the agent, the freelancer, who is of more limited means. As for the principals, we enforce individual rationality. It means that each principal's expected utility, value minus payment to the agent, is non-negative. This guarantees each principal's participation. Throughout, we'll refer to limited liability as LL and to individual rationality as IR. Third is the challenge of coordinating multiple principles. This intensifies both problems above, since now, not only is there asymmetric information between the principals as a group and the agent whose action is hidden, there is also asymmetric information among principals themselves. Since each principal have different privately known value for each outcome, their interests may diverge. The classic literature on multiple principles has thoroughly explored one class of contracts, where each principal independently sets forth a payment scheme to the agent and pays accordingly. We refer to these type of contracts as first price contracts, reminiscent of first price auctions where each bidder pays her bid. We show that first price contracts can be very inefficient in terms of social welfare. And this is not so surprising since in these type of contracts, there is no coordination among principals, and it can cause the agent's choice of action to differ from what is in the joint principal's interests. To be able to coordinate all principals, we consider more sophisticated contract formats. Specifically, we study what is called contractable contracts, in which the payments of one principal can depend on the contract submitted by the other principals. And our premise of this talk is that contractable contracts will enrich contract design for multiple principals, just as auctions beyond first price enrich auction design for multiple buyers. More than that, we'll see that the computational toolbox will be very instrumental in realizing this potential. So now I'm going to get into our model that formulates a game that allows us to consider more sophisticated contract formats beyond first price. So what do we need for a model? We have an agent and we have multiple principals. The agent has a set of actions available to him. Each one bears a cost and stochastically results in an observable outcome. We assume that the probability for an outcome given an action is publicly known. So the weights on those edges are publicly known. Then, as mentioned before, principals have different private values for different outcomes, and this whole valuation profile is assumed to belong to a prescribed domain referred to as the valuation domain. So this is the basic setting, and now we need to define what is a contract. What we want from a contract is to generate payment scheme that incentivize the agent to take a desirable action, which we denote with A star V. We focus on welfare, where the welfare of an action A is the sum of principal's expected value given action A, minus the cost that the agent bears by taking action A. A star V will be the action with the highest welfare. A contract will be a mapping from the valuation profile into outcome-specific payments. It formally consists of n functions from the valuation domain and the outcome set to R. So all in all, the game proceeds as follows. First, since principals' valuations are privately known to every principal, all principals simultaneously give their reported values, referred to as their bids. A bid for an outcome is supposed to represent the principal's maximal willingness to pay for that outcome. Each principal submits a bid for each possible outcome. Then, their bids are mapped according to the contract into outcome-specific payments. And based on that, in the second step, the agent chooses an action, X star B, that maximizes his expected utility, payment minus cost. Finally, an outcome is realized, and each principal pays the agent according to the contract's payments. Recall that we enforce two standard properties of contracts. First is limited liability. It means that we have non-negative payments for the agent. And second is individual rationality. It means that each principal has non-negative expected utility. As mentioned before, the classic notion of a contract in common agency is what we refer to as first price contracts. In these contracts, each principal independently sets forth a payment scheme to the agent. In our model, it simply translates to having each principal paying her bid, so having each T equal to the corresponding B. First price contracts satisfy individual rationality and limited liability. However, it suffers from inefficiency when considering social welfare. We study the efficiency of first price using the adhered measures of price of anarchy and price of stability. Beginning with price of anarchy, we show that the price of anarchy of first price contracts tends to zero when the number of principals tends to infinity. So informally, it means that the worst equilibrium welfare in first price is infinitely worse than the optimal welfare. Also, we show that the price of stability of first price contracts tends to half when the number of actions tends to infinity. And again, simply put, it means that the best equilibrium welfare in first price is as 2 times worse as the optimal welfare. To remedy the inefficiency of first price contracts, we suggest a new class of contracts called IIVCG, which, similarly to their namesake, the renowned VCG mechanism, guarantee welfare maximization. So a contractee is an IIVCG if the following holds. First, the agent maximizes the reported social welfare. And second, the expected payment formula of principal L is of the following form. Some function H that is independent of principal L's bid minus the welfare of others. In this type of contracts, we have the same trick on payments as in VCG. So by the same commonly known arguments, we have that principals are induced to bid truthfully as a dominant strategy. So principals' bids reflect their values, and since the agent maximizes their reported welfare, we get as a corollary that every IIVCG contract maximizes social welfare in a dominant strategy equilibrium. This is a great starting point. First, dominant strategy truthfulness is a significant advantage of IIVCG over first price contracts. Since in first price contracts, it is unclear how the principals arrive at an equilibrium. Further, by being so close to the VCG mechanism, we can apply a well-known uniqueness result and show the uniqueness of the IIVCG class. Specifically, we show that every contract such that the agent maximizes welfare and that induces truthfulness by the principal is an IIVCG contract. So all well and good, but the definition of the IIVCG family raises some challenges that have no parallel in the mechanism design world. First, the agent needs to be incentivized to maximize social welfare. He's not a social designer, and we cannot force him to maximize social welfare. Second, we only have a formula for the expected payments. A contract must determine payments for every possible outcome realization. We tackle these challenges by providing a complete characterization of the outcome-specific payments that incentivize welfare maximization by the agent. I won't get into the details of this lemma for the sake of this talk, but I will mention that this lemma is useful since it exactly defines our design space. In particular, it translates into linear constraints that are the cornerstone of our algorithmic construction we will shortly present. So we have a characterization of IIVCG contracts, and we know that they satisfy truthfulness and welfare maximization by the agent. But what about the other desiderata of individual rationality and limited liability? How do we choose payments from this design space such that these properties are satisfied? Actually, our results reveal that there is an inherent trade-off between individual rationality and limited liability. While it is always possible to find an IIVCG contract that satisfies one of these properties, either limited liability or individual rationality, in some common agency settings, there is just no IIVCG contract that admits both of these properties. So combining limited liability and individual rationality, that is protecting both sides of the market simultaneously, raises some surprising issues. To overcome this impossibility result, we leverage our characterization and use it constructively. We design two polynomial time algorithms. One receives as input a common agency setting and determines whether or not there exists a truthful welfare maximizing contract that is both LL and IR. If such a contract exists, the second polynomial time algorithm implements it. Specifically, it receives principal's bits profile and the stochastic resulted outcome as an input, and it computes the contractual payments on the fly for every principal. Refer to this mapping of algorithm 1 as algorithmic IIVCG. Note that there is a conceptual difference between algorithmic IIVCG and the classic contract functions, given by a closed form formula. However, every deterministic algorithm can be viewed as a function, and indeed, our algorithm 1 yields a contract. Further, the algorithmic basis of algorithm 1 gives us the flexibility to protect both sides of the market that may not exist when trying to use a closed form formula. So just to wrap up, we saw that the classic contract formats in common agency, first price contracts, are inefficient. We define a family of socially efficient contracts, IIVCG, completely characterize them, and show their uniqueness. We revealed an inherent trade-off between limited liability and individual rationality. And to remedy this trade-off, we introduced algorithmic IIVCG and designed two polynomial time algorithms. One determines whether or not there exists an IIVCG contract that is both limited liability and individual rationality for a given setting, and the other implements it if such a contract exists. In the future, one can extend this model to multiple agents and can ask about randomness or think of contracts that guarantee both limited liability and individual rationality, but only approximately achieve the optimal social welfare. This is pretty much it. Thank you so much for listening.